Hello everybody, my name is Apurva and today I'm going to be showing you different types of infinities. Okay, so everybody knows about infinity, I hope at least. So everybody thinks there's infinity and there are some weird properties like infinity plus 1 is infinity and lots of other weird stuff that infinity can do. What you might not have known is that there are two types of infinities. And I'm not kidding. You might be like, what? No. How can there be two types of infinities? There's infinity, and if you multiply it by anything, you still get the same infinity. But indeed, there's a bigger infinity, which you cannot get by doing operations. No amount of operations. It's like trying to do this. It's like trying to do x and saying x plus something else will give you y. Now, x and y look completely different, right? You cannot get them by operations. It's a completely different thing. Like how 2 and 1 you can add and subtract, but that's not how it works with infinities. Because anything plus infinity and stuff is infinity. Anyways. Okay. So let us begin. First, we need to find what infinity are we talking. So what are these two types of infinities? So there are two types of infinities. One of them is the counting infinity, and n is the symbol for counting, and then there's a real number infinity. R is the symbol for real. So there are technically 5 stages of the way numbers are used. N, Z. Now obviously these are not the exact symbols. Like for example, Z has like a extra line here, but I'm just telling in basic. So there are 5 sets of numbers. Sorry. N, which is the counting numbers. Z, which is the integers. Q, which is the rational numbers. R, which is the real numbers. And C, which is the complex numbers. Today we'll only be getting into these four. Complex is a little bit more complicated. But still, the real number and complex numbers are usually equal. Anyways. Right now, we're not getting into the complex number part. We're just sticking to the real numbers and below. So first are the counting numbers or natural numbers, which are 1, 2, 3, 4, etc. Not 0, because you do not count with 0. That's why it's called counting numbers, and these numbers have existed from a very, very, very long time. I mean it, like from whenever numbers were created, these numbers were used because they were used in real life. Zero is never really reused, and a concept of zero didn't come till much, much later. Neither did negative numbers. So, this is this, and now this is clearly an infinity, right? I mean, you could just keep going on and on and on and on and on, right? Am I correct? So, next up, I'm going to show you how that. So actually, what you might think is because I told you all these different number types, and forget about C right now because that's not important. N, Z, Q, and R. Natural integers, counting integers, rational, and real. So, here's the thing. You might think that, oh wait, this is one infinity, this is one infinity, this is one infinity, and this is one infinity. No. These three are actually equal. And actually, even though there are more numbers included in the number set, the infinity is still the same. But this infinity is infinitely times larger by an infinite amount times larger. And I'll show you that in a moment. So what does it mean for two things to be equal, and how does that make any sense? So to show that as well as normal numbers, like if there are 5 apples and 5 oranges, the way we show that they are equal is for every apple there is an orange. We are able to make a partner. So there will be 5 of these pairs, which shows that they are the same. Even with number sets, say you have the number set of 1, 2, 3, and you have this number set 4, 5, 6. They have the same amount of items in the set because we can pair them each up equally without having anybody who does not have a partner. So that's how we show that they are equal. So now we're going to show how the countings infinity set and the integers infinity set are equal. So let's write down. So first, or we need to first write these in an order, the integers. Well, if you think of it, it's pretty common sense because we can write 0. Oh wait, that's eraser. 1. And we can't, because then now here's the problem. We can write 0, 1, 2, 3, but then we forgot all the negative numbers. Let's say 0, 1, -1, and then 2, -2, 3, -3, and so on, so on, so on. 3, negative. You know what? I'm just gonna stop at 3. Dot, dot, dot. So now that we've ordered them up, you can see that we can each have a matching pair 2 to 1, 3 to -1, 4 to 2, 5 to -2, 6 to 3, blah blah blah. And each of the next ones will pair because we sorted them. So this clearly shows that they are equal. Nobody will have a lost partner. And actually the same way some other people have also proved things such as, okay, you know what, I should have just funded it all of the extra markings. Oh wait. No, 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 no. Okay. Yes. Okay, there we go. So, somebody, so now this is actually how we can also show that the set of all even numbers is the same as all counting. Like if you just take 2, 4, 6, 8 and pair it up with this, they'll be the same. Even odd numbers you can show. You can even show, for example, all the square numbers 1, 4, 9, blah blah blah. All of them will have partners and they're the same infinity. They're all the same infinity. The counting infinity. That's why I'm gonna write this N. The counting infinity. Now, next up, we are going to talk about rational numbers. What does it mean to be rational? Meaning you have a decimal place that either terminates or has a repeating pattern. So, for example, 1/2 is just 0.5. It is rational or can be expressed in a fractional form with an integer on top and an integer on bottom, except the bottom cannot be 0 obviously for obvious reasons. There's something divided by 0 is explosion. Actually it's not explosion, it's infinity and negative infinity at the same time. Both of them are answers, that's why there's no actual finite answer, which is why we say undefined. Anyways, back to where we were. So 0.5 can be expressed as 1 by 2. But pi, which is 3.14, blah 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 blah, blah etc. Okay, all of that 3.14, blah blah blah. Dot 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 dot. Okay, so this entire chain can never be expressed as a fraction. We can keep now. Everybody's taught that pi is 22 by 7. It's approximately. And we can keep trying to get closer and closer fractional estimates according to how fractions work and etc. But we can never ever really reach pi. Ever. Like we can never get a 100% accurate value. Pi is just pi. It is not rational. You can never express it as a form, a set of z upon another set of z. And the bottom can't be that. And even 1/3, even though it is an infinitely trailing digit, it can be expressed like that, and the pattern repeats. It's not a randomly non-repeating pattern. Any decimal that has a completely random pattern does not belong to the set of Q or rational numbers. Or the second definition, which is as of it cannot be expressed as an integer upon another integer. So now if they have to be the same, first we need to be able to sort it. And for a long time people thought that there was no way to sort this out. But there is. So what we can do is using the sums of both of them. So let's start with the sum of 0. Yeah, it does not work. So instead of 0, 1, blah, 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 we will list them in order of their sum. So sum of 0 is 0.0, but that's undefined, so we're not writing that. So what fraction can give a sum of 1? 0 upon 1. Yes, that is the fraction. And that's the only fraction because 1 upon 0 is invalid. So 0 upon 1. Okay, and then -1 we can get by 0 upon -1, but that's again the same thing. Oh yeah, also There are actually infinitely many possibilities like this. Because that way then 1 can also be expressed, because the sum can also be expressed as -1 by 2. But here's the thing, you can take any of these fractions and just multiply them by a negative factor. So we can say only counting numbers and 0. So 1 upon, not 1 upon 0, 0 upon 1, 0 upon 1. Then the sum which involves 2, which is 1 upon 1. And now we don't need to include 0 after the first step. So that will be 1. Next up, it is the sum of 3, which is 1 upon 2 and 2. So that's different, 1 upon 2 and 2. And anytime, honestly, we can just rewrite them. So we can write this, then it's negative counterpart, this negative counterpart, this negative counterpart. And you can technically do this all the way till infinity. Again, you can pair this up because I've sorted them. Negative half and 2, and then for 3 it's 1. And then for the sum of 4, my bad, will be 1 plus 3, 2 plus 2. And 2 plus 2 we're not rewriting because that is 1. And 3 plus 1. So 1/3 and 3. And then we'll get 1 by 4, 2 by 3, 3 by 2, 4. And so here we'll get, and then so on, so on, so on. You guys get the pattern, right? And then next we'll ignore the center one because that'll be 3 upon 3, etc. Basically, they all sum up. And because we can match them, and then we can add the negative counterparts right after, right? I have not shown it here, but it can be 0 and negative counterpart not needed, 1, and then -1, etc. But you can clearly match them up, which explains why it's also the same infinity. Now, why is the real infinity not the same? This is completely different. So for a long time, people are like, what? No, they have to be the same. I mean, come on, even though there's no way to sort real numbers, and there isn't, by the way, guys. Everybody thought that, yeah, what's the big deal? I mean, come on, how can they be different? And I mean it. And it's not just the whole real set. I can even prove it to you even more easily. The amount of numbers between 0 and 1, obviously in real, is more than the number of counting numbers. 1, 2, 3, obviously. It's even more than the integers, if you want to say. It's even, oh yeah, and by the way, in the rational set, all rational numbers, meaning all the integers are there. And even in the real set, there are the fractional answers. Okay, so we cannot forget those. Even they do exist, yes. But for our representations, even if we forget them, so the amount of numbers between 0 and 1, not equal to 0 and 1, okay, the amount of numbers here is infinitely more. And I will show you how. So let us begin. Then counting numbers, and since we know that, okay. Anyways, so since we know that the counting numbers and the integers and all are, and the real rational numbers, sorry, my bad, are the same, I'm just gonna write the counting numbers for simplicity's sake. 7 dot dot dot. Okay. And now some real numbers, and I'm going to say purely irrational numbers right now, not even real. Irrational numbers fall in the real set, but that means I'm excluding all fractional answers. 0.333, those will not exist. I mean, they can, but anything terminating is not going to be in this list. So let's say 0.672898657 dot dot dot. Obviously, because they're not terminating. Then the next one can be 130493637 dot 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 dot. And we can clearly see that say the next one is 0665288 5, 0, 3, 1, dot, dot, dot. You can clearly see I can come up with an infinite string of numbers and we'll be able to pair them up, right? Right. Okay, so I'm just gonna write 4 more of these. This is such a... Okay, so let's say 2, 5, 9, 6, 8, 7, 3, 1. 3, 1, 2. Dot, 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 dot. Let's see. 3, 3, 2, 9, 7, 3, 5, 4, 0, 6. Dot, dot, dot. Trying to be as random as I can. Anyway, it's okay if they're not random because such systematic numbers like that above must exist. At least initially, and then they get randomer. Anyway, 2 more numbers. Let's see. You can skip this part if you like and just scroll to the part where I'm talking again. Like, not talking, but talking about how this is not possible. So clearly, as you can see, we can pair them up, obviously. Let's 4, 6, 2, 1, 4, 0, 0, 1, 5. Dot, dot. Last number 5, 2, 8, 1, 7, 7, 3, 5, 0, 1. And so here we have the numbers. Okay, and so now, I might have actually done extra on the numbers. Yeah, I did. Okay, I drew. Okay. You know what? For simplicity's sake, I am erasing all this extras because they're not there, and the trailing dots are there. Okay, and so now here's the magic. And you can clearly see we can pair them up equally, right? And this is just irrational. So you're like, but now here's the catch. Even though they're just irrational numbers, what the heck happened to all the rational numbers? We have exhausted every irrational number and everything in Q and stuff is still left. So A, that's number 1. So A is a bigger infinity. And B, but then you're gonna say, okay, fine, the real number infinity is our infinity plus an infinity. So technically, by this statement, I am saying that 2 infinity is bigger than infinity, which is rubbish, technically. But it kind of isn't rubbish, right? Because, I mean, see, this is clearly infinity, all of the rational numbers, right? So I'm saying that infinity plus infinity is bigger than infinity, which is rubbish. They're actually the same. But now here's the catch: it isn't. Because I can act. So now you might think, because of the rational numbers thingy. But still, by common sense, you can just redo this up. Like say you alternate each one and then put each of the rational numbers in between. You still get it. Okay. But I'm still keeping them outside. It's okay. But do you know why I'm keeping them outside? For this very reason. So I'm going to create a completely new 1, 2, 3, 4, 5, 6, 7, 8, and I'm only showing the first 8 digits. I'm going to create a completely new irrational number that is different from all of them. Okay, and here's how. So I'm going to look at the first digit of the first number. Okay, and I'm going to write something else. I can write any digit as long as it is not the first digit. Like as long as it's not 6, because that's the first digit of the first number. So I'm just gonna write 2. And now 2, of the second number, I have to make, for the second digit, I will make sure that the second digit is different from the second digit of the second number. Okay. So I'll make that 9. It's not the same. And now for the third digit, I'll make sure it's different from the digit of the third number. And so I'll make that 7. And for the fourth number, I'll make sure the fourth digit is different for this. 1, 2, 3, 4. So the fourth digit, I'll make it 0 if I want. And fifth digit of the fifth number is 3. So I have to make sure that this is not a 3. You guys are black. What? Why is he doing this? And the sixth digit here is 0. So I'll make this an 8. And the seventh digit of the seventh number is a 5. Is a 5. So I'll write a 4. And you guys get the point. The 8th digit of the 8 number is that dot dot dot. But now you guys might be like, ha ha ha. Okay, you have made a number like that. Now, why should it be different? So you guys tell me, okay, what number do you think? If you say that the 1000 and the 1000, and there might be a number which looks like this, okay, and it looks identical for say the first million digit, but say the number million and one in this list, because million and one here, if you see its partner, the million and first digit of that number will be different from this. Why? Because I made sure that the millionth and one digit is different. So it is not possible, and therefore I can actually create another set. Instead of 0 to 9, that I can make 0, 3, 0, 3, 7, 3, and you guys get the point, right? I can just create an infinite set as long as the the first digit is not the same as the first digit of the first number. The second digit is not the same as the second digit of the second number. And so that way, no matter which number you call out, that digit will be different. So if you find your list and say the billionth and second number is different, the billionth and second is the same, it's not true, because the billionth and second digit will be different. So this clearly shows, this clearly proves that it is another scale of infinity, because this I have already said is a set of real numbers, so that's infinity, right? I've said that, and now I added that extra infinity of that, but that's still infinity, so no. And then I add another infinity, because that's another set of infinite of these numbers, but there's a huge amount of infinity that's unparalleled. You cannot re-squeeze it in an alternation, because if you okay, wait, some of you guys might come up with an argument. Okay, you created that set of extra list. Now just squeeze it in. So say alternate. So move this to this, move Say you're going to move each one to all the even numbers. So just move the number here to here, move the number here to 4, move this to 6, move 5, move 4 to 8, etc. So all of them are on the even slots, and then you put this new set. But I can still create another infinitely more, and another more, and another more. And you can never ever stop enough, because I can create infinitely, infinitely more sets. Like imagine an infinite set of infinite sets, and you might be like, yeah, that's also infinity. Apurva, really, that's also infinity, right? Yeah, okay, fine, that might be, but I have so many infinite sets. I have this very infinite sets, and I have infinite sets. I have infinite raised to infinite raised to infinite, never terminating. It just blows. There is no way you can fit an infinite set. And that's why the infinite of real numbers is never ever going to ever be the same as the infinite of natural numbers. They will never be the same ever, because you can keep on and on and on and on and on generating, no matter how many times you multiply infinity, square it, raise infinity to infinity, etc. times. Then and only then, and infinite times. And I mean it infinite, until it goes on and on and on, then you will reach the real amount. The infinite of infinite, etc. of infinity. This number is an infinitely huge constant times larger than this infinite. In fact, nobody can ever say how large it is. 1 second. Okay, anyways. So this shows that clearly that the infinite of real numbers is very big and very different from this infinite. And now they both might have the same properties, like if you multiply the real infinite by 2, you will still have the real infinite. But they are still not the same infinites. And this is like something like a different scale altogether. There is no imagine saying that there's no operation that you can do to 0 to get 1. Obviously that's not true. But in this case there is, right? Because this real infinite is a infinite of your unlimited infinites. Like infinite of this, but that times infinite. So basically an infinite loop of infinites is basically what it is. So that's why the set of numbers of infinity. Now, many people think of infinity as the highest number, but instead you should think it of the number of numbers instead. That's what really infinity is. And this infinity is different from this because the set is overall larger than this other set. Okay, thank you guys for watching. Please subscribe to my channel to support me. Like this video if you like it. And last but not least, click the notification bell so you don't get missed off of another video. Bye everybody.